Okay, so in this video I'm going to talk about velocity and acceleration and momentum, and these are level 3 questions. So the first question is about the difference between distance and displacement. Okay, so remember, distance is a scalar quantity, and scalar just have a magnitude, which is a number. Okay, so that might be 10 meters or 5 kilometers. Displacement is a vector quantity, and vectors have a magnitude, so I'm just going to write m for magnitude, and they also have a direction. Okay, so that'll be north, south, east, or west. Okay, so remember, one has a direction and a magnitude, and the other one just has a magnitude. Use figure 1 to determine the displacement of the train in travelling from A to B. Okay, now if we were to work out the distance we'd have to measure this whole line. So the best thing to do would be to put a piece of string over the line and then expand the string out and measure the whole thing. That would be the distance, but it's not asking us to do the distance, it's asking us to do the displacement, and the displacement is always the shortest path between 2 points. Okay, so between those 2 points with a ruler you would measure those, and if you measure those I get 7.5 centimeters. Okay, and now it's also asking you the direction, and the direction is north and that is east, so it's 7.5 centimeters. Okay, northeast. Now it's asking you in kilometers, and 1 centimeter represents 5 kilometers. So if 1 centimeter equals 5 kilometers, then 7.5 multiplied by this factor of 5 is going to give us 37.5 kilometers. So the answer is 37.5 kilometers, and the direction, as we said, is northeast. Okay, now how would we know the angle? Because it's a vector, we need to be more accurate. So how would we know the angle? Okay, so from this point here we need to measure this angle. Okay, and that is 62 degrees. So it's 62 degrees northeast. So I'm going to put in there 62 degrees. Okay, remember, for vectors you often have to use the angle, and it's 62 degrees from north and it's going east. Right, the next question. There are places on the journey where the train accelerates without changing speed. How can this happen? Well, acceleration, remember, is a change in velocity. Okay, so anything that changes velocity must accelerate. Now the next question is, what does velocity mean? Well, velocity is equal to the speed of an object and its direction. So if we change either of these, we must change the velocity. Now we're not changing the speed, but we are changing the direction. If we change the direction, we are changing the velocity, and if we change the velocity, we are accelerating. So you need to put that into a sentence. Okay, so a change in direction causes a change in velocity, and a change in velocity is equal to acceleration. Acceleration is defined by a change in velocity. Okay, this next question. Estimate the distance travelled by the train along the section of journey shown in this. So velocity and time, if we multiply those together, we get the distance travelled. Okay, so 100 times by 5 is the area of 1 square. So 1 square is equal to 5 times 100, sorry. So that is equal to 500 meters. So the area is equal to 500 meters. Now the best thing to do is to then work out how many squares you've got. So we've got 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 squares. Now we need to work out the half squares that we've got. Okay, so this is half a square. Okay, this one you'd have to say is half a square. This one is 3/4 of a square, and this one is a quarter of a square. So all those would equal 2, and that one would be a half and a half, roughly speaking. So that means you've got a half plus a half, which is 1, a third, 3/4 plus a quarter, which is 1, and a half plus a half. So we've got 14 squares, and we're going to add it to these 3 little squares, so that gives us 17 squares. We're going to multiply that by the distance of our area of 1, which is 500. 17 multiplied by 500 is going to give you a distance travelled of 8,500 meters. Okay. So the next question is about aerodynamics. It says the go-kart always had the same mass and used the same motor. The change in shape from the design X to the final design Y will affect the top speed of the go-kart. Okay, so we know that the mass is the same and they use the same force, so we're not going to talk about mass and force, but we do want to know about the top speed. Okay, so we're going to say mass and force are constant, so the only other factor that affects speed is air resistance. Design Y, if you look at it, it's got a pointier shape, so we say is more aerodynamic. Okay, that means a pointier shape, it's going to cut through the air better. So design Y is more aerodynamic, so has less air resistance. Okay, and if you have less air resistance, then the force pushing this way will be less. Okay, so this one's going to have a lower force than this one. That means that it's going to have a higher terminal velocity. So design Y is more aerodynamic, so has less air resistance, and therefore has a higher terminal velocity. Okay. Right, the final design of go-kart Y is entered into a race. The graph shows how the velocity of the go-kart changes during the first 40 seconds of the race. Use the graph to calculate the acceleration of the go-kart between points J and points K. Give your answer to 2 significant figures. Okay, so we've got here a velocity of 5. Okay, so we're going to have our end velocity, which is 5. Remember, acceleration is equal to v minus u over t, and 5 is our end velocity. Our start velocity is 0, so 5 minus 0. I'm going to divide that by the time taken, which clearly is there, and that is equal to 3. 5 minus 0 is 5, divided by 3 will give us our answer, and that is equal to 1.7. And that is already 2 significant figures, so I'm going to put 1.7 as 2 significant figures. Okay, use the graph to calculate the distance the go-kart travels between points J and points K. Okay, so we're going to look at this area travelled in terms of the graph. Okay, so we know the points are from there to there, and this is a triangle. So we've just said that the time is 3, and we're going to multiply that by the velocity, which is 5, okay, because that gives us the side. So this as a triangle would be 3 times 5. Now 3 times 5 would give us the whole area if it was a rectangle. So because it's a triangle, we only are interested in this part, so we're going to have to divide that number by 2. So 3 times 5 is 15. If we divide that by 2, we will get 7.5 meters. Okay. What causes most of the resistive force acting on the go-kart? That's going to be air resistance. Okay, a car driver sees the traffic in front, is not moving and brakes to stop his car. The stopping distance of the car is the thinking distance plus the braking distance. What is meant by the braking distance? So it is the distance travelled. The distance travelled from pressing brakes to actually stopping, so to stopping. Okay, this is the important point. It is the distance travelled, not the time taken. Don't write the time taken. The braking distance of a car depends on the speed. So they've given us the speed, so we can't use that. And the braking force, state one other factor that affects the braking distance. So that could be condition of brake pads. Okay, you could talk about weather conditions, but if you say weather conditions, make sure you say icy or wet roads. Okay, be specific. How does the braking force needed to stop a car in a particular distance depend on the speed of the car? Well, if we increase, so increased speed is going to require a greater braking force. Okay, that makes sense. The faster you go, the more force you will need to stop the car. Okay, so it says use figure 1 to calculate the maximum speed the car was travelling just at in general, not at any point, so at in general. So we're going to look on this for the steepest part of the graph, and that is clearly this part here. So we're looking at where it is directly proportional, which is around this point here. Okay, now we need to make sure it's definitely directly proportional, so we're going to pick a part of the graph where we know for a fact that it is directly proportional. Okay, so if I go across from here, I'm going to pick this point here, I'm going to pick 1, 2, 5, I'm going to go across. Okay, and I'm going to go across from 175 as well. Okay, so I know for a fact between these values it is directly proportional, so I don't need to select a bigger amount because I know this is where it is a straight line. This is definitely the fastest part of the graph. Okay, so I'm going to subtract these two numbers. So that goes to this point here, which is not quite 175, it's at 170. So the line actually finishes at 170. So 170 minus 125, and that's going to give me 45. Okay, so that is my y-axis. And I need to divide that by my x-axis because I'm looking for the gradient. Remember, y over x, the change in y, should I say, over the change in x is going to give me my gradient. So we've got the change in y, that is equal to the change in y. So what's the change in x? Well, if you draw a line down from where it hits the line, make sure you're using a ruler and the same there, then you're going to get 8 and 10. But we're going to do that the other way because we're going to subtract. So 10 minus 8 is equal to 2. So that is equal to the change in x. So we'll write that up here. Now we know that our gradient is 45, and we're going to divide that by 2 because that is y, that is x, and that will give us 22.5 meters per second. Okay, so that is the maximum speed. That is where this point here is the maximum. So remember, we must do the change in y divided by the change in x. Okay, the car did not stop in time. It collided with the stationary car in front, joining the cars together. The momentum of the two cars was conserved. What is meant by the statement, momentum is conserved? So that means the momentum before a collision is equal to the momentum after a collision. Okay, so the momentum before a collision is equal to the momentum after a collision. Calculate the velocity of the joined cars immediately after. So before they collide, this is going to give us our momentum. Okay, so we're looking for the momentum of the whole system. That is everything here, and that will tell us the momentum of the system after the collision. So we're after all of this first. So we're going to do P, which is momentum, is equal to M times V. And normally we'd have to do it for both of them, but because this is going 0 meters per second, we know 900 times 0 is going to give us a momentum of nothing. So there's no point working out the car because the overall momentum of the car is 0, so it doesn't matter. So all we really need to do is the momentum of this vehicle. So we're going to do the mass, which is 1500 kilograms, and we're multiplying that by 8 meters per second. Okay, so if we work that out, that gives us 12,000, and we're going to use that unit kilograms and that unit meters per second. So we put them together. Now we have the momentum here. We know the combined momentum of all of that is 12,000. So therefore this has to be 12,000 based on our definition. Before the collision is equal to after the collision. They have to be the same. Okay, so now we can use that. We know that P is equal to 12,000, and that is equal to the mass times the velocity. Well, what's the mass? The two cars are joined, so we know it's both their mass, so we need to do 1500 plus 900, and that is equal to 2,400. Okay, and that is multiplied by V, but V is what we're trying to find out. So if P is equal to M times V, then we know that V is equal to P divided by M. Our momentum is 12,000. Our mass of both them joined together is 2,400. So we're going to do V is equal to 12,000 divided by 2,400. And that will give us our answer. And that is equal to 5 meters per second. Okay. Right, this next question is only for triple physics. So I'm going to explain it anyway, but you don't need to answer this question if you are doing the combined course. So it is safer for a car driver to be wearing a seatbelt compared with not wearing a seatbelt if the car is involved in a collision, and you need to know why. Okay, the reason for that is there is going to be a lower force. Okay, now why is there going to be a lower force? Because there is it's basically because of the rate of change of momentum. Okay, so there is going to be a lower or slower rate of change in momentum. Okay, so the force acting on anything is due to the rate of change in momentum. So what do I mean by this? Well, imagine that the momentum was 1,000 kilogram meters per second. The speed at which it takes to go from 1,000 to 0 when the car has stopped is going to be the size of the force. So if this happens very quickly, say that happens in 0.01 seconds, you're going to have a very large force. If that rate of change happens very slowly, say it takes 2 seconds, then you're going to have a much smaller force. Okay? So basically, if you have a seatbelt, it will slow the driver down, and therefore the rate of change in momentum is going to take longer to go from a high momentum to a low momentum. If you have a slower or decreased rate of change in momentum, you have a much smaller force. Okay? So without seatbelt, rate of change in momentum is much greater, so force is large. With seatbelt, the rate of change in momentum decreases, so force is lower. Okay, just imagine that if you jumped off something very high, say you had a cliff and you jumped off the cliff, if you jump straight onto a floor, you're going to go from 50 meters per second to 0 meters per second instantly, and therefore the force on you is going to be very, very large. Instead of that, we have a bouncy castle, and you jumped onto the bouncy castle, and it compress, slowing you down. So from this point here, you are slowing down. So you can see that you've gone from 50 meters per second to 40 to 30 to 20 to 10 before you hit the floor. So by slowing down the rate of change in momentum, you're going to have a much lower force. So the bouncy castle would decrease the force on your body, whereas hitting a concrete floor, the rate of change would be so quick that you'd probably kill yourself or break your legs. Okay, so that's what that means. Right, this next question. Explain using the idea of momentum why the skateboarder moves backwards. Okay, so remember our definition we just talked about. The momentum before any collision is equal to the momentum after a collision. Okay, so that's the first thing we're always going to write in this kind of question. So momentum before collision. Okay, in this case, the action that's happening is equal to the momentum after the collision. Okay, so that's the first point. Now the overall momentum before he jumps off is equal to 0. So therefore the momentum after he's jumped off must be equal to 0. Okay, so overall momentum before equals 0 kilogram meters per second. So it must equal 0 kilogram meters per second after the collision. Okay, that's really important. So if it equals 0 here, when he jumps off, so using the idea why the skateboard moves backwards, the skateboard moves backwards as the skateboarder jumps forwards. When he jumps forwards, he now has a momentum. Let's give him a momentum of, say, 5 kilogram meters per second. That means that the skateboard has to have a negative momentum of minus 5 kilogram meters per second. They both have to even out. They have to cancel because the overall momentum after leaving must equal 0. So we're going to say to conserve momentum of 0, the skateboard must have a negative velocity if skateboarder has a positive velocity. Okay, now remember you can't have negative mass, so the reason this is going to be negative is because the velocity part is negative. Remember, velocity is a vector, so if I decide that this way is positive, then this way has to be negative. It doesn't matter which way is positive and negative, but once you've decided that one way is positive, the other way becomes negative, and it's it's not the momentum, it's the velocity that is negative. Okay, right, the mass of the skateboard is 1.8 kilograms and the mass of the skateboarder is 42 kilograms. Calculate the velocity at which the skateboard moves backwards if the skateboarder jumps forward at a velocity of 0.3 meters per second. Well, we've just said that before the collision it's equal to 0, after therefore must be equal to 0 because they have to be the same. Okay, so we know our equation is P equals m times v. Okay, if the mass of the skateboard is 1.8 and the mass of the skateboarder is 42, it says calculate the velocity at which the skateboard moves backwards if the skateboarder jumps forwards at 0.3. So we know we can do the skateboarder because we have all the information we need. We have the mass and the velocity. So the skateboarder is 42 kilograms. I'm going to times that by his velocity of 0.3. Okay, and that will give us 12.6 kilogram meters per second. Well, we said that the momentum has to equal 0. So the momentum going forwards is now 12.6. The momentum going the other way must be minus 12.6 kilogram meters per second. Okay, so now we've got the momentum minus 12.6 kilogram meters per second. And we know that the skateboard's mass is 1.8. Then we can rearrange this. Sorry, that's a multiplication for V. So V is going to equal to P divided by M. So that's equal to minus 12.6 divided by 1.8. And that will give us the answer of 7 meters per second. Now it's really minus 7 meters per second, but in your exam they're not really worried about negative signs, but the real answer is minus 7 meters per second. Okay, a paintball gun is used to fire a small ball of paint called a paintball at a target. The figure below shows someone just about to fire a paintball gun. The paintball is inside the gun. What is the momentum of the paintball before the gun is fired? Well, if it's stationary, it has to be 0, but put a unit meters per second. Okay, give a reason. As I've just said, it is stationary. Remember, anything that isn't moving cannot have a momentum. Okay, moving on. The gun fires the paintball forwards at a velocity of 90 meters per second. So we know that P is equal to M times V, and that mass is 3 kilograms. And we're going to times that by 90. And if we do that, we will end up with 0.27. Okay, so the answer there is 0.27. The momentum of the gun and paintball is conserved. So the total momentum of the gun and paintball just after the gun is fired will be equal to the total momentum of the gun and paintball before the gun is fired. Okay, so this next question, a car is driven along a straight road. The graph shows how the velocity of the car changes during part of the journey. So you can clearly see here that it's going positive 12 meters per second, and then at 6 seconds the speed decreases, or the velocity decreases to 0, and then here we've got a negative velocity. Now we could think of this as a 400 meter track, so they've clearly at this point here going forwards, and then at this point we could say they're turning around the track, and until this point here they'd be there, and then at this point here they've got a negative velocity, so that is when they'd start to be going the other way. Okay, and they'd be increasing their velocity, but they're not going quite as fast, and then they'd be going at a constant speed. So remember, you've got a positive velocity and then you've got a negative velocity. So think of it like that. That's kind of what this is showing. Okay, so use the graph to calculate the deceleration of the car between 6 and 9 seconds. Okay, so it's talking about between this point here and this point here, and we're going to use A equals V minus U divided by T. Okay, so what is V? That's our end velocity, which is 0. What is U? That's our start velocity, which is at 12. Okay, so 12 and 0. And then how long did that take? Well, it's taken from 6 to 9 seconds, so that is 3 seconds. So 0 minus 12 is minus 12, and we divide that by 3, and we will get a deceleration of minus 4 meters per second squared. Again, you don't need to use a negative number, but if you go and do A-level physics, it'll be helpful if you get in the idea of using these now. Okay, at what time did the car change direction? Well, I talked about this idea if it was a 400 meter track, that at this point here it's obviously changing direction, so that's when it starts to become negative. So the time is at 9 seconds. Okay, so a bus is taking some children to school. The bus has to stop it a few times. The figure below shows the distance time graph for part of this journey. Okay, so this is not a velocity time graph, it's a distance time graph. So don't get confused, because it's quite easy when you're doing the distance to think, oh, I'll work out the area. Well, that would be for a velocity time graph. So how far has the bus travelled in the first 20 seconds? You just have to look at this, and that is at 20 seconds, so that tells you it's 100 meters. Describe the motion of the bus between 20 and 30 seconds, so that's between these 2 points. Okay, so motion is 0 meters, it is stationary. Okay, so the bus hasn't gone anywhere. It's clearly at 100 meters there, and it's still at 100 meters there. There's been no change in distance. Describe the motion of the bus between 30 and 60 seconds. Well, when you get a curve on a distance time graph, it means it is accelerating because there is a change in velocity. Okay, this is showing a change. That's why we've got a curve. What is the speed of the bus at 45 seconds? Okay, so for this we need to draw a tangent. Okay, so you need to first of all go to 45 seconds, which is between, so we're going to 1, 2, 3, 4, 5, which is there. Okay, now when you do this, it's obviously easier with a pencil and ruler. You must use a pencil and ruler. Now you need to draw a line for this. Okay, so you're going to draw a line that represents that part here. And it's going to look something like that. Okay, now the bigger you make the line, the better. Okay, but it's going to be something like this. Okay, so you've got to draw a line against the curve. This is called a tangent. Now when you've done that, you draw your lines across and you're going to show the change in y divided by the change in x. Okay, so you've got lines that go across something like that and lines that go down from there. Okay, so what's the change in time? Well, that's the change in x. The change in time is 60 minus 30, so that's from this point to this point here. That is our x-axis, so that is our change in x. Okay, and our change in x is obviously equal to 30. Our change in y, now when you do this you must use a pencil and ruler, so when you've printed this out and you've done it properly, you should get a distance, which I worked out, of 180. So it should have gone, this line should be at 180, and you need to subtract that. If you did this line properly, it'd be at around 75, so to subtract it from 75, so that's going to give you the change in y. So 180 minus 75 is 105. Okay, so now we've got that. Remember, speed is equal to distance divided by time. Our distance is 105. Our time taken is 30, so 105 divided by 30 will give you 3.5 meters per second. Okay. Right, later in the journey, the bus is moving and has a 500,000 joule kinetic energy. The brakes are applied and the bus stops. How much work is needed to stop the bus? Well, if it's got this much energy when it's moving, to stop it, you will need that amount of energy because energy is conserved, so that is going to be equal to 500,000 joules. The bus stopped in a distance of 25 meters. Calculate the force that was needed for it to stop. Okay, so the force, work done, is equal to force times distance. We know that this is the work, okay, so work is 500,000, the distance is 25 meters, so if we rearrange this equation, if work equals force times distance, then force we're after must be equal to the work done divided by the distance. So what's our work? 500,000, and we're going to divide that by 25. 500,000 divided by 25 gives you 20,000 newtons. Okay, what happens to the kinetic energy of the bus as it is braking? Well, if you remember, we've got this store of kinetic energy, and that store of kinetic energy is going to be transferred to a different store, and that's going to be the thermal store. So this is going to end up with no energy in it, and the thermal store will have all the energy. Okay, so what happens to the kinetic? So the kinetic energy store is transferred to the thermal store. So we've gone from KE to thermal. Okay, so kinetic energy store is transferred to the thermal store. Okay, this heats up brakes, tires, and surroundings. Okay, so they're the things that are going to get hot. The brake pads are going to apply to the brakes and they're going to get hot. The tires and the friction of the road, so the grip, the rubber on the road will get hot, and this will then heat up the surroundings. So the road will get hotter and the air particles around these things will also heat up as well. Okay, so this next question is back to momentum again. So it says the drawing below shows two railway trucks A and B moving in the same direction. So remember, when they're going in the same direction, we add the momentum. If they're going in the opposite direction, then we take the momentum away. Right, so it says truck A catches up and collides with truck B. The two trucks become coupled as shown in the diagram. Calculate the initial momentum of truck A. Well, we know that it says here that is equal to A. P is equal to M times V, and that is equal to 1500 times by 8, and that will give you 12,000. The momentum of truck B is equal to 1 times 2000, so that gives you 2000. Okay, the total momentum of the trucks before the collision must be these combined, so it's the whole momentum. Remember, we do the whole system, so we just add them because they're going in the same direction. We've got one here that is 12,000 and one here that is 2,000, and if we add those two together, we will get a momentum of 14,000 kilogram meters per second. Okay, the next question says calculate the speed of the coupled trucks after the collision. Well, we know momentum before is equal to 14,000, so we're going to say the momentum after must be equal to 14,000. Okay, P is equal to M times V, so velocity must be equal to P divided by M. We know our momentum after the collision is 14,000 kilogram meters per second, which we just got from here. It says the coupled trucks. This means they are together. You can see in the diagram they're both together, so we're going to divide that by the mass of both of them. So that is 1500 plus 2000. Okay? So what is that equal to? Well, that's equal to 14,000 divided by 3,500, and that will give you 4 meters per second. Okay, how is the total kinetic energy of the trucks changed as a result of the collision? A calculated answer is not needed for full marks. Well, we know the kinetic energy of the trucks must decrease. Why must they decrease? Because when they collide, you're going to get energy given out. There's heat and sound. Okay, you know, there might be even be lighted. There's a few sparks when they collide, so that has got to decrease. So the overall kinetic energy of this system here, when they're moving afterwards, must be less, and the reason for that is because there is, so it says state and energy. Well, I would go for heat given out during collision. Okay, so figure 1 shows the forces acting on a rocket, and you can see the direction of movement. How does the velocity of the rocket change as the rocket moves upwards? Okay, so the velocity is going to decrease. Give a reason for this. Well, that is because there's going to be some air resistance. Okay. Now, a lot of people think that when it's fired, it's going to start speeding up, and that's not the case because there's no force on it. The only way something can accelerate is if there is a resultant force. The only force that's going to happen on this model rocket will be at the very beginning when it's fired. So when it's fired, it's going to have an instant force, and that's going to cause it to accelerate. But as soon as that's happened, there is no force. So the air resistance is going to increase and increase and increase, and eventually the air resistance is going to push it down, and it's going to go up, and it's going to come straight back down again. Okay, so the velocity has to decrease instantly. As soon as it's fired, there is no longer a force pushing up. There is only forces pushing down. There'll be air resistance and weight pulling it back down again. The velocity of the rocket is not the same as the speed of the rocket. What is the difference between velocity and speed? Well, we talked about this before. Velocity is a vector, okay, and that has a magnitude and a direction. Speed only has a magnitude. Okay, the speed of the rocket just after being launched is 12 meters per second. The mass of the rocket is 0.05 kilograms. KE is equal to half times mass times velocity squared. Okay, so that's equal to 0.5, and we're going to multiply that by the mass, which is 0.05, and we're going to multiply that by 12 squared, Remember, you need to do this first, okay, and that will give you an answer of 3.6 joules. Okay, as the rocket moves upwards, it gains gravitational potential energy. State the maximum gravitational potential energy gained by the rocket. If you ignore air resistance, if it has 3.6 joules of kinetic energy, then when it gets to here, it must have 3.6 joules of gravitational energy. It must gain as much as it had before, because energy is always transferred. Remember, this is a conservation of energy. Okay, calculate the maximum height the rocket will reach. Well, we know that GPE is equal to the mass times G times the height. So we've got our gravitational potential energy, which is 3.6. We've got our G, which is 10. We're after H. So we're going to rearrange this. So if we're multiplying by M and G, then the inverse is to divide by M times G. That cancels, that cancels. We need to do the same on the other side. So we know our equation height is equal to GPE divided by mass times by G. So what's our GPE? It's 3.6. I'm going to divide that by the mass, and the mass is down here in the question of 0.05. And we times that by G, which is 10. Okay, and if you do that, you'll end up, I'll just cover that up here. Please show your working out in the exam, and 3.6 divided by 0.5, and that will give you an answer of 7.2 meters. So that's how high it's going to go. Okay, figure 2 shows 4 velocity time graphs. Taking air resistance into account, which graph A, B, C or D shows how the velocity of the rocket changes as it falls from the maximum height it reached until it just hits the ground. Okay, write the correct answer in the box. Okay, so you're going to start up here, and when it starts to fall, the initial velocity here is that it's going to be 0 meters per second, and as it falls it's going to accelerate. So we need a graph that shows an initial velocity of 0 and then an acceleration. Now as it accelerates, air resistance is going to increase and increase, and the rocket is going to reach terminal velocity. So you can see this graph shows 0 to start with, an increase in velocity shows an acceleration, accelerating, accelerating until it reaches this point here. There is no change in velocity, terminal velocity reached, so the answer is B. Okay, the rocket can be launched at different angles to the horizontal. The horizontal distance a rocket travels is called the range. What pattern links the angle at which the rocket is launched and the range of the rocket? Okay, well you can see that as we increase the angle, the range increases up until 45 degrees. So increasing angle to 45 degrees increases the range. Any increase past 45 degrees in angle causes a decrease in range. Okay, so we put 2 points because it's got 2 marks, and we talked about the range up until 45 getting bigger and bigger, and then past 45 you can see the range has decreased. Okay, so this next question, it says when the toy is hovering in midair, the fan is pushing 1.5 kilograms of air downwards every 10 seconds. Before the toy is switched on, the air is stationary. Okay, so it's told us force is equal to a change in momentum divided by the time taken. So we need to work out what in this equation we already have. Okay, so do we have a mass? Yes. So we know that the mass is equal to 1.5 kilograms. Okay, we need to look at anything else that we might have. So we know that the weight is 0.69 newtons, so that is a force. So we know we've got the force, and that's equal to 0.69 newtons, and we know that that's equal to a change in momentum. So we need to work out our momentum, which is 1.5 kilograms, and that's going to be multiplied by the velocity. Now we're after the velocity, so we're just going to put v here. I'm going to divide that by the time taken, which is 10. So we've got 1, 2, 3 parts of an equation, so we can rearrange this now to find the final part. Okay, so if we're dividing by 10, then we're going to multiply, so 0.6 multiplied by 10 would give us 1.5 times v. So we now know that to move this across, we can divide that by 1.5, and therefore v is equal to this. So 0.6 times 10 is going to be 6, and 6 divided by 1.5 is going to give our answer of 4 meters per second. Okay, explain why the toy accelerates upwards when the fan rotates faster. Okay, if the fan rotates faster, you're going to have it generate a larger lift force. So the lift force increases when fan rotates faster. Okay, why is this important? Well, if you have a greater lift force than you have a weight, what do you get? You get a resultant force, and if you have a resultant force, you get acceleration. Okay, so the second part of this question, this causes an upward resultant force. Make sure you don't write RF, make sure you write that down in your exam, and therefore acceleration. Okay, remember, if you ever talk about a resultant force, you must always say there is acceleration in the direction of the resultant force. Okay, the toy is not easy to control, so it often falls to the ground. Explain how the flexible polystyrene base helps to protect the toy from being damaged when it crashes to the ground. Okay, so this is the same as the answer I did previously. It's a physics only answer, so if you're not doing triple physics, you don't need to know this. Okay, so what does the foam do? The foam reduces time taken to stop. How does it do this? Well, it's because of that rate of change in momentum again. So I'm going to just do this quickly. So this is due to a slower rate of change in momentum. Now remember, if you have a lower or slower rate of change in momentum, you get a much lower force. So the force is down to the rate of change in momentum. So if you go from 50 kilogram newtons to 0 quickly, you have a great force. If you do it slowly, the force is much less. Okay, when two objects interact, they exert forces on each other. The forces are equal in size and act in opposite directions, which is that one. Right, this next question, describe the motion of the boat. Well, the first thing is we work out the resultant force. So they're in opposite directions, so it's going to be equal to 300 minus 250 because they're going opposite, and that gives us a resultant force of 50 newtons. So the resultant is that way 50 newtons. That's the overall force. If you have a resultant force, we've just discussed it, what do you get? A resultant force is acceleration, and it will accelerate to the right. So it always accelerates in the direction of the resultant force. When the boat reaches land, the resistive force increases to 300 newtons. The fisherman continues to exert a force of 300 newtons. So we've got a force there of 300, got a force that way of 300. What's the overall force? 0 newtons. And if you have no resultant force, it travels at a constant speed. Okay, so constant velocity to the right. It's not going to slow down, it will just keep going at the same speed that it was going until another force acts. Okay, so when forces are equal, objects continue at a constant speed in a straight line because there is no resultant force. Always talk about resultant force. No resultant force, constant speed in a straight line. If you have a resultant force, accelerates in the direction of the force. Okay, moving on to the last question. So this is one of those vector diagrams. In this final question, it's about vectors, and you can see there's a 300 Newton force that way, which I worked out as 3 centimeters. So if that one is 3 centimeters, that has to be 3 centimeters because they're the same size force. When I worked out the angle, I worked out that that was 40 degrees. Okay, so we need to put these two vectors together. So we've got a 300 Newton force that way. So you measure a line that's exactly horizontal at 3 centimeters long with a ruler. Okay, now from that point, you're going to measure, if we just put some angles on it, this angle here has got to be 40 degrees. So using your protractor, you need to draw a line down there, okay, that from this point is 40 degrees, and it must be 3 centimeters long, which is going to get to about there. Okay, so we can get rid of that. Okay, and then we can finish that off. So we know that that vector would come to there. Now this is going to give us our resultant vector. Remember, we put the tip and tail together, and when we join them from this point here to this point here is our resultant vector. So in a different color, just going to draw my resultant vector, which is there. That is the resultant force. So we now need to measure this. If you measure it, you'll get 5.6 centimeters. Okay, and we know that 1 centimeter is equal to 100 newtons, because before 3 centimeters was equal to 300 newtons. Okay, so 5.6 must be equal to 560 newtons. So our answer is 560 newtons. That is the size of the resultant force. Okay, so in the following slides are the answers that you can use if you've just done the exam questions without any help.